So the next section is about data. So we'll do a little bit more in the details of how we transform data, how we pre-process the data, and how to bring the data as an input for deep learning models. So this is a simplified picture of the data lifecycle in general. I have reality, which is super complex. Like we cannot understand reality in its whole. And what we will do is use sensor to extract information, partial information from reality. And we will do measurements, and we will measure some features from reality. And this feature will be organized as example. And we will see the definition of these concepts in the next slide. So this feature will be pre-processed. I will obtain some representation that we call local representation. I will give it to my model, and the model will output other representation that will be given to a decision maker that will make some actions in reality. And then I recover new data, and you can see the global picture. So what is an example really in a concrete way? So an example is a set of data that is self-contained, independent, and identically distributed. So let's take an example to see these three concepts. We will study flowers, the iris flowers. It was a data set used by the famous statistician Ronald Fisher in 1936, and this data set was gathered in the Appalachians, I think, in Gaspésie, and also close to the border of the US. So we were already gathering data in Gaspésie for machine learning in the 30s. So for this example, we can see that if I ask to a biologist what are the features required to predict the species of an iris, I have 3 different species for iris, and I want to measure some feature. I don't want to use all the information of this flower, but only some few features to predict the species of the iris. The biologist can tell me, you just need 4 features: the width and the height of the petal, and the width and the height of the sepal. With these 4 measurements, you can already know what is the species of this flower. So if I take one flower and measure these 4 features, this example is self-contained. I have all the information necessary with probably a little bit of noise, but I have enough information to predict my label. Here I have also the notion of independence. So the way this example occurs in reality, it should be as independent, as much independent as possible to the other examples. So probably you should not gather all your data set from your garden, because of the type of ground that you are using, your features will be correlated together. The petal width and the petal height will have the same distribution in your garden, but if you go to another place, maybe the distribution will not be the same. And it's just because it's the underlying process that is generating the flowers that is not independent. And identically distributed, it means that you should cover all possible iris flowers possible in the world. It's not only they should be independent, but you should cover any variation of the iris flower where you want to use your model. So if you go to another country to use your model, you should probably go to this country to retrieve some data to train your model. Only relying on the generalization capability of your model to use it in another country where the iris can be very different can be risky. And how we will structure an example is as a couple of variables. So we will have the feature here as an X, and the labels or the targets that we want to predict as a Y. So here I have my 4 features. I can represent it as a vector of 4 elements, and here I will have one label among 3 to define the species of the flower. So some difficulties with independence. Let's say I have a time series over 1 day. So it's measurements over the day. And I want to give the whole time series to my model to predict if this time series is normal or not normal. And if I don't have a lot of data, what I can do is to take sub-part of this time series. So my test was for time series over the day, but because I don't have enough data, I will cheat a little bit and use this part that I will use the label associated for all the day. I will use the target here, I will assign to this sub-part, and I will put it in the training set, and this part I will put it in my test set. And what can happen is that there are temporal correlation between the two, and if my model is using just the temporal correlation inside the day to make a good prediction, then the result for this one will be good on the test set. And in fact, the model is using features that it should not use because it's only occurring inside the day. And I have temporal correlation between the two examples here. It's not independent. So what I can do if I really don't have a lot of data and I want to use this technique is to add a buffer between the time series, to try to remove the temporal correlation inside this time series. But it's risky, again, because I don't know the length of the buffer that I should use. And now an expert in data for this particular data set maybe can help you to decide what is the minimum length that I should use to remove the temporal correlation so that the model will not cheat by using the correlation inside the day. Same thing for images. If I want to predict something on these huge satellite images, and I begin to extract sub-patch of it, and I put this sub-patch in the training set and this one to the test set, I can have spatial correlation. It's the same idea than before, but it can happen in 2D or in any dimension of your data. So as soon as you're taking one example and extracting subpart to create artificially new example, there is a risk that you should be aware of the model cheating by using these correlation. And again, you can use a buffer, but be sure that that you are removing the spatial correlation. And it depends on the test. If the test is really about this city in the world and you want to learn something about this city, you can use patch that are close. But if I want to train a model on this city and to use it for another city in the world, using sub-patch inside the same city can be tricky because I'm not sure if the features used here will generalize to a new city because I'm evaluating in the test set the model over the same city. Okay, now the difference with identically distributed. Let's say I want to recognize object in images. If I'm just using images in winter in Montreal, the data distribution of my pixel will look like this here. And if I want to use this model over all the year, then you can see that the data distribution of the pixel here is very different. Here I have mostly white pixel because of the snow. Here I have colorful pixel because we are in fall. And if I'm just training my model on winter images, then it will probably not generalize to any other season because I'm just training my model on one part of the overall data distribution. If I want to make it identically distributed, I should gather images over all the year because this is the time span over which I want to predict with my model.